As we continue looking at linear functions, we find ourselves at 5.3, slope-intercept form. Our objective today is to graph linear equations in slope-intercept form. And we can see that shows up in this particular situation about bamboo growing very quickly. The graph here on the side models the growth of a bamboo plant. Find the point where the line crosses the vertical axis. What does this point tell you about the bamboo plant? So as it crosses the vertical axis right here, that kind of tells you something. Find the slope of the line. What does the slope tell you about the bamboo plant? Kind of as it's changing each time, what does that tell you something? So we're going to practice these concepts a little bit here. Let's do some review. When I get to each question, what I'm going to do is you can go ahead and just press pause, work it out yourself, and then see how you did. So what is the slope of this line? Now it's because I'm using rise over run. I'm going to see that from the point 2, 1, it rises 1 and runs 1. So the slope is 1, 1. I could rise 2 and run 2, slope 2, 2. It all comes down to my slope is 1. On this one, you can press pause and try this one out. All right, so we're going to rise to run. My slope starting just from this point, it rises 2 and runs 1. I can check a couple different points here. It rises 4 and runs 2. So my slope in this case is 2. What is the y-intercept point for this line? Y-intercept is where that point intercepts the y-axis. So the point right here, if we look at the point itself, it's at 0, -2, and this point right here is our y-intercept. So our y-intercept is -2. What is our y-intercept point for this line? The coordinate here is 0, 1. It's going to be this point right here. So this point intersects at 1, which tells us that our y-intercept indeed is 1. What is the slope and y-intercept for this blue line? Okay, we've looked at horizontal lines and the slope for this line. If we look at rise over run, it is 0. It does have a y-intercept though. It does cross its intercept line at 2. All right, I'm going to read a couple things. Keep track of this stuff. A family of functions is a group of functions with common characteristics. So it's a group of functions, right? A parent function is the simplest function with these characteristics. So simplest would just the simplest looking one, the one with the least complexity to it. A linear parent function is y equals x, or the function of x equals x. The graphs of 3 linear functions are shown at the right. So we've got a bunch of linear equations there. The parent function is the simplest function, so we're looking at that guy right there is probably the parent one, the main one, and the linear parent function is also that one because it's not just the parent function, but it's the linear one. It indeed creates a line. A linear equation is an equation that models a linear function, okay, creating a line, nice consistent amount, and a linear equation. The variables cannot be raised to a power other than 1. So y equals 2x is a linear equation. And we found this out. If you square x, or even look at this particular situation, these ones are not linear. When you graph them, the line either curves or it v's or it changes. It doesn't continue to move at a constant linear pattern. Graphs of a linear function may cross the x-axis at any point. The y-intercept of a graph is the y-coordinate of the point where the graph crosses the y-axis. Essential understanding here, you can use the slope and y-intercept of a line to write and graph an equation of the line. And we're going to go try that out here. So we're going to take a look at slope-intercept form of an equation of a line. Okay, so linear equation, it's going to be a nice line, is y equals mx plus b is our slope-intercept form. Now this is interesting. Now we've worked with something that looked like this, y equals kx. Now this was true when we were looking at a direct variation. And when this happened, k right here, we use k to represent the constant. of variation. Okay, but when we start working something out with it as a constant, we use the variable m to represent the slope of the line. So k represents the constant of variation because this indeed right here is a direct variation, whereas up here in this particular situation, we use m to represent the slope. It is not a direct variation, and it also isn't a constant of variation. So keep track of the letters here. So we have a k and we have an m. Both of them are coefficients of my x. The y-intercept is also going to be b. Okay, so there's my y-intercept when it's playing out. And we can see it over here. So my slope is 2, as represented as my coefficient. It goes up, rises 2 and runs 1. So it's 2 over 1. And then my y-intercept plays out at 3, shows up in my equation, and it also shows up in my graph at the point 0, 3. Find the slope for the equation where y equals negative 6x plus 5. You got it? Negative 6. Find the y-intercept for the equation y equals negative 6x plus 5. The y-intercept is a 5. Did you get it? Nice. There's my slope. There's my y-intercept. Let's try it again. Find the slope for this equation. Y equals 3x minus 7. The slope is going to be 3. My y-intercept is going to be negative 7. And be careful because sometimes we flip our 3x and our negative 7. So make sure you're looking for the coefficient on this one. Here's probably the guts of our lesson today. The steps for graphing and using y equals mx plus b. M being my slope, b being my y-intercept. You're going to write the function in the form. In function form, we're going to isolate y. So y equals. You're going to find m and b by simplifying. You're going to plot b. This is the third thing. You're going to plot b, which is your y-intercept. And you can remember b is where you begin. B is where you begin. It is your y-intercept. And then you can use m, which is your slope, to plot 2 more points for this line. And you can remember m is how you move. Yeah. Draw the line through the points. And when you draw that line, remember this represents a solution. So use a straight edge, a book, a note card, just something to get a nice consistent pattern. You use 3 points because 2 points will get you a line. The third point will tell you if you're going in the right direction. We're going to graph the equation. Y equals 1/4 x plus 2. M in this particular situation is 1/4. My y-intercept is 2. So I'm going to start at 2 is my y-intercept. It's right there. And my slope is 1/4. So I rise 1 and run 4. 1, 2, 3, 4. And there's my next point. I rise 1 and I run 4. 1, 3, 4. And that's going to be my line right here. Graph the equation. 3x plus y equals negative 2. Now remember, for my first particular point on the thing, I have to solve in terms of y. So I'm going to subtract 3x from both sides. I have y equals negative 3x minus 2. Once you press pause, and you give it a try. And then press play and see how you did. All right, how'd you do? My y-intercept is at negative 2. And my slope is negative 3 over 1. So I rise negative 3, which means I drop. And I go over 1. And it's a negative slope, which is telling me it is going to decline as I go left to right. A couple things on my graph I want to keep an eye on, and I want you to do that as well, is when you graph a line, it should be straight, and you want to put arrows on the ends to indicate that this solution does continue on beyond my graphing points. Use slope and y-intercept to graph this equation. Again, why don't you give it a try? I'm going to press pause, and let's see how you did. All right, I have a nice straight line. I'm putting arrows on the end. Now in this graph I did a little different. I extended the lines all the way to the edges of the graph. That's something I would also like you to do when you're graphing a solution on a graph. Notice when I'm looking at my slope, or my m being negative 2, I'm thinking of it as negative 2 over 1. My slope is declining as I go. All right, press pause, try this one, and let's see how you did. All right, my slope is 1, which is rise 1, run 1. Get my arrows on the end. My y-intercept is at -3. I got to turn this into a function, so let's do that first. So minus x, so I have 2y equals 6 minus x. I'm going to divide everything by 2 and end up with y equals 3 minus x over 2. I'm going to change this around though so I can see it in slope-intercept form. It's going to be, this is negative here, so it's negative 1/2 x plus 3. I'm going to pause this and graph it, and you can see how it's going. All right, take a look. Let's see how we did. Negative slope of 1/2. At 3 is the y-intercept. For parallel lines, let's think about how that's going to happen, how the slope ends up being, and how the y-intercept ends up being. And we're going to take a look at these two equations. So show that the lines whose equations are 2x plus y equals 8 and 2x plus y equals 6 are parallel. I'm going to look at them in y-intercept form first, and maybe that'll let us see what's going on with that. I'm going to grab this one and look at it over here. 2x plus y equals 6 minus 2x minus 2x. Y equals negative 2x plus 6. And if I plot these two on a graph, I'm going to actually do a quick little plot. So I'm going to pause. All right, I'm back. Now when I look at these two, the linear relationship that's happening in the red, it shows that the y-intercept is at 8, and the other one is at 6. So they have different y-intercepts, but their slopes match. And because their slopes match, these two equations are going to continue and they'll never reach, and thus they are parallel. So let's look back here. So parallel lines, the slopes are going to be equal, but the y-intercepts, they could be different. We just got to keep an eye on that. And that will look at parallel lines. Let's see what else we got here. We're going to show that the lines whose equations are these two options, that they are parallel. So I'm going to rewrite them, put them in y-intercept form, and take a look at their slope and their y-intercepts. So let's press pause and take a look. All right, when I look at these two equations and I play them out, I can see they do have a different y-intercept. In fact, this one doesn't have a y-intercept, so we can look at that as k, vector variation. But they both do indeed have the same slope, and because they have the same slope, they will never meet, and thus they are parallel. So you can start to see these things before we even graph them. When you have two equations playing out and you're looking at them, if they have the same slope, no matter where they start on their y-intercept, they won't meet each other. All right. Well, good luck. You keep practicing. I'm going to go eat my shoe.